Okay, dear colleagues, let us start our BIM's Integrable System seminar session. And today our speaker is Mizuki Yamaguchi from University of Tokyo. Okay, please share your screen.
Yes.
Okay.
Thank you very much for introduction. And it's my great honor to talk in this seminar. I'm Mizuki Yamaguchi from the University of Tokyo. And in today's talk, I would like to, as title say, I would like to classify some quantum spin chains into integrable systems and non-integrable systems. And this is today's contents. And today's talk is based on two results uploaded on arXiv. First, let me clarify the precise meaning of some terms. And in this talk, we characterize the integrable systems and non-integrable systems by the number of local conserved quantities. Here, local quantity means that it is written by a sum of operators acting on a few consecutive sites. For example, this quantity, the sum of x, y, z on successive sites, is a three-local quantity. And another example is the sum of zi xi plus 4, which is counted as 5 local quantity. So here, locality means spatial locality. And local conserved quantity is order 1 local quantity, which is commutative with the Hamiltonian. And famous example is this 3 local quantity, which is commutative with the Heisenberg chain Hamiltonian. And integrable systems are known to have an infinite number of local conserved quantity. By contrast, non-integrable systems are defined as the system without local conserved quantities. And obviously, there is a huge gap between the definition of them. So we refer to the system with finite number of local conserved systems as partially integrable systems. And importantly, it is strongly expected that almost all systems are non-integrable. The one evidence of this fact is the consistency with empirical laws of macroscopic systems. Non-integrability is a necessary condition for some empirical laws such as the Kubo formula in linear response theory and thermalization and normal heat conduction. And let's take a look at thermalization. And thermalization is a phenomenon where the value of observable reverts to its equilibrium value. But the local conserved quantity of integrable systems is have a time invariant value, so integrable systems never thermalize. And another evidence is numerical simulations, which mainly focus on the energy spectra. And from these evidence, it is many researchers expect that almost all systems are non-integrable. But it is difficult to prove the non-integrability for some systems. And it was even out of scope of mathematical physics until 2019. A breakthrough of this topic is the non-integrability proof on the XYZ model with a magnetic field. Shiraishi shows rigorously that this model is a non-integrable system. And the second result is on mixed field Ising model, and PXP model and next nearest neighbor Heisenberg model are also shown to be non-integrable. And here, let me clarify the research question of mine. From 2019, some models are shown to be non-integrable, but these previous studies deal with some specific systems, and there is no general result classifying the integrability and non-integrability for broad classes of systems. So the non-integrability, the ubiquitousness of non-integrability is not proved yet, although it is widely believed. So let's go to the first result. And in the first result, in the first study, we consider general spin half chains with symmetric nearest neighbor interaction. In other words, the general one-dimensional system of spin half particles and whose Hamiltonian is composed of the nearest neighbor interaction term and the magnetic field terms. And the Hamiltonian is translationally invariant and parity symmetric. We consider the old systems satisfying these conditions. And explicitly, the Hamiltonian is described like this. And this class of systems include both of integrable systems, which are already known, and some non-integrable systems which are shown by recent previous studies. And here is the main theorem of our result. We rigorously show that the models in this class are generically non-integrable in the sense that they do not have non-trivial local conserved quantity. And the only exception is the already known integrable systems. And this result is the this study is the first result to prove the ubiquitousness of non-integrability. And it is also proved that there are no overlooked integrable systems which remain to be discovered. And moreover, it is this result also shows that there are no partially integrable systems with a finite number of local conserved quantities. So that means that the class of in these systems classified clearly into integrable systems with infinite number of local conserved quantities and non-integrable systems without a local conserved quantity.
Could I ask?
Yes.
So without any, so we have only Hamiltonian and nothing else, yeah? In all the cases except of integrable.
Yes, Hamiltonian is exceptional quantity, and there is some magnetic magnetization could be local conserved quantity, and we show that for k is greater than 3. So Hamiltonian is 2 local, and the magnetization is 1 local. So these quantities are exceptional. Non-integrability can have that kind of local conserved quantity.
Yeah, so it means if you have a model of this class and you have the third, something like third Hamiltonian, or third power of S, or XYZ, third power of your spin variables, you will have an integrable system. So this follows from this theorem. Is it true? Yeah. If you have some higher Hamiltonian, at least one, you have an integrable system.
Sorry, what is sorry, please repeat the question.
If you have some Hamiltonian which is short power of your spin variables, so the model is integrable. Yeah. If you have at least one non-trivial integral, it is integrable. Yeah.
At least one, what?
At least one non-trivial conserved quantity.
Yes.
For example,
Sorry.
short power of your spin variables.
Our definition is integrable systems mean that infinite number of local conserved quantity, and finite is defined as partially integrable systems.
Yeah, so you don't have the case when you have only one non-trivial, so only zero or infinite, yeah?
Yes.
Okay, thank you.
Thank you very much. And sorry for my yes. And let's go to sorry. Then we go to the proof preliminary part, which simplify the Hamiltonian. And this is the original Hamiltonian we treat. And here, the interaction matrix J is a real symmetric matrix because of the parity symmetricity. So this matrix J can be diagonalized by the replacement of the basis, which is called global spin rotation. And by global spin rotation, the Hamiltonians get to have a more simple form. And here we notice that the global spin rotation does not change the integrability of the system. So because the global spin rotation is just a replacement of basis for each side, so the number of local conserved quantity does not change. And here we divide the cases. Into according to the number of non-zero elements in coupling constants Jx, Jy, and Jz. It is also called the rank of the matrix J. And so there are four cases, rank 0 case, rank 1, rank 2, and rank 3 cases. And the reason why we divide in this way is because the proof strategy is quite different depending on the rank of J. And after that, we see the fact. And this is the table of classification of integrability and non-integrability for rank 0 and 1 and 2 cases. And this is the table for rank 3 case. And all we need to do is to prove the non-integrability of the system, which is not shown to be integrable or non-integrable in the previous studies. So our work is this one and this one and this one. And then go to the proof idea. The non-integrability proof is based on a very simple idea. First, we expand arbitrary local quantity Q like this. And here A is a basis element of local quantity. And QA is a coefficient of this. And the set of the QAs specify any local quantity Q. And then we consider the commutator of Q and H, and the commutator of Q and H is also a local quantity, so we can expand this commutator by the basis of local quantity. And here, the taking commutator with the Hamiltonian is a linear map, so we can that this coefficient RB is can be written by a linear combination of QAs. And conservation condition is the commutator of Q and H is equal to 0, so which means that the old coefficient RB is equal to 0. And these conditions gives a linear system of linear equations of QAs. And as explained in the former slide, non-integrability is identified as the absence of local conserved quantities, so which is equal to the absence of solution of the system of linear equations of QAs. This slide is all about the idea of non-integrability proof. So non-integrability proof is based on a very simple idea, and non-integrability proof is just a problem of linear algebra. And the natural question arises here is that what the basis of local quantity is. And the answer is local Pauli strings. And Pauli strings is a tensor product of Pauli operator of each side. And the local Pauli string is the Pauli string whose non-trivial support is local. And for example, the basis of one local quantities is the set of xi and yi and zi Pauli operators. These are for each site number I and the identity. And the basis of two local quantities include the basis of one local quantity and plus xx on successive sites and xy blah 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 zz. And the basis of three local quantities is the basis of two local quantities plus xxx and xxy and and ziz. And we denote the operators on each row as A1i and A2i and A3i. Hereafter, we use this symbol, so please remember this A notation, just a symbol for operator. And another important issues is how the linear map of taking the commutator with the Hamiltonian is represented by our basis. And in order to answer this question, let me consider the commutator of basis elements. That means Pauli strings. And for example, we consider the commutator of these two Pauli strings. And we notice that these two operators have an overlap only on the site number I. So the answer is like this. So it is important that the commutators of Pauli strings other Pauli strings unless they are commutative. And in order to visualize this commutation relation, we introduce a column expression of the commutator. So in the column expression, the first row represents the first argument of the commutator, and the second row represents the second argument of commutator, and the final row, last row, represent the output of the commutator. And here we assume that the first argument is a term in local quantity Q, and the second term is a term in the Hamiltonian. And go back to the previous slide, and we expand the general K local quantity like this. And we found that basis of local quantities is local Pauli strings. And notably, the commutator of Q and H is at most K plus 1 local quantities. That is because Q is K local quantity and the Hamiltonian is 2 local quantity, and the term of them must have an overlap on some sides in order to be non-commutative. And concretely, our mission is to show that all K local A operator have zero coefficient for K local conserved quantity. So in this figure, our mission is to show this is equal to 0. So after showing this is 0, this quantity Q is no longer K local conserved quantities. That means the absence of K local conserved quantities. And we showed the absence of K local conserved quantity for general K, which is rather than 3. So after all, we proved the absence of all non-trivial local conserved quantity. And here we shortly remark that we cannot conduct this proof for K equal 2 because there is a trivial local conserved quantity such as the Hamiltonian. And then we go to the proof detail part. And due to the time constraint, we focus on the rank 2 case, which means that the coupling constants Jx and Jy have non-zero value, and Jz is equal to 0. And in the rank 2 case, we can easily show that this A operator, z blah 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 x, has 0 coefficient. And we can be convinced of this fact by considering the contribution to this B operator, z blah 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 zy. And this B operator is generated by the commutator of this A operator and YY interaction at this position. And the important fact is that this B operator is generated only by this commutator. Let me explain the reason. And so the first argument is at most k local, and the second argument is at most 2 local, because they are term of the Q and Hamiltonian respectively. So and in order not to be commutative, there are only 2 possible forms of commutator generating k plus 1 local B operator, like this one and this one. And take a look at the left form, and focusing on this side, we can show that this operator is 0. Sorry, Z. But take a look at the Hamiltonian. There is no Z interaction. So this form of commutator is impossible to generate this B operator. And in the right form, we can be convinced that this operator is Y. And take a look at the Hamiltonian. This second argument must be Y-Y interaction. And focusing on this column, this secret, the commutator of this secret operators, Pauli operator, and Y becomes a Z. So this secret operator must be X. And after all, this is the only possible form of to generate this B operator. And this is exactly the same as this. So we can conclude that this equation holds. And we have that Z blah 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 X operators have 0 coefficients. So hereafter we repeat this kind of discussion. So if there is something unclear, please feel free to ask me a question on this slide. Not only on this slide. Okay. So let's go to the next slide. And we can also show that Z blah 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 Y and Z blah 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 Z also have 0 coefficients. And to convince of the former fact, we consider this B operator which is generated only by this commutator. And another possible form of generating this B operator is like this, but there is no Z interaction in the Hamiltonian. So only this commutator generate this B operator. And the similar discussion holds for the latter case, and because there is no Z interaction. So the lesson of this slide and the slide just before one is that if A operator is if the leftmost operator of A is Z, then its coefficient is equal to 0. Okay. And then we next we consider this XX blah 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 X case, and this the commutator of this XX blah 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 X and YY generates this B operators, B operator, and another possible form of generating this B operator is like this. But take a look at this column, and the commutator of secret operators and X becomes X, but there is no such Pauli operator. So it is also impossible commutator to generate this P operator. And similar discussion holds for this xi blah 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 x case, focusing on this column. The commutator of no Pauli operator and x becomes the identity, so it is impossible. And in this slide, we consider the case that the rightmost operator is x or y, but sorry, x. The rightmost operator is x, but we can repeat the similar discussions if the rightmost operator is y or z. So we can conclude that if A operator is started with xx or xi, then its coefficients is equal to 0. And next, we consider the case A operator is xy blah blah blah. And this case is slightly more difficult than the previous slides. By considering this B operator, there is two commutators which generate this B operator, like this one and this one. And from this, we can obtain these equations, include two contribution. And here we notice that this coefficient, this operator is started with z, so this coefficient is equal to 0, which we shown in the previous slide. So we can conclude that this xy blah 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 x also has the 0 coefficient. So after all, we can obtain that if A operator is started with xy, then its coefficient is 0. Let us review our findings so far. First, we show that if A operator is started with z, then its coefficient is 0. And next, we show that xx blah 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 and xi blah 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 have 0 coefficient. And after that, we show that xy blah 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 also has 0 coefficient because it is proportional to the coefficient of z blah blah blah, which is 0. And in the rank 2 Hamiltonian, x and y play almost equivalent role, so we can we can also prove for by switching x and y. So we can prove that yy blah 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 and yi blah 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 and yx blah 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 also have 0 coefficient. And the remaining is are these. By repeating the similar discussion, we can also show that these kind of operators have 0 coefficient. And we repeat this kind of discussion again and again and again. We finally observe that except for these operators, all the other operators have 0 coefficient. And the exception is exceptional operators have x or y in the leftmost side and x or y on the rightmost side. and the sequence of z, 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 z in the middle. And we also have we also obtain that these remaining coefficients satisfy this kind of linear relations. For example, we can convince of the first equations from by considering these commutators. And at this time, we have obtained all the equations of QAs, which is corresponding to the K plus 1 local B operator. So in order to prove that this remaining coefficient is 0, we must consider the K local B operator. And let's go to the final step of our proof. And warning that this step is the most complicated part of our proof. And so we focus on the k equal 5 case. And we show the coefficient of y, z, 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 y is 0. And to show it, we consider this B operator, y, z, z, y, y, which is generated by these two commutators. And this operator is our target operator. But this x, z, y, y operator is kind of garbage operator, or obstacle operators. So we want to delete the effect of this operator. So in order to do it, we consider another B operator, which is generated by these three commutators. So this obstacle term again appears here. So this xgyy operator, xgy's coefficients can be offset. But we notice that there is another obstacle operators appear here. So we consider we again consider another B operator, which is generated by these two commutators. And consider the equations which is correspond to this B operator. So there are three B operators. So we have three equations like this one, this one, this one. And we can if we sum up these equations by with appropriate factor, we can delete this red obstacle coefficient and blue obstacle coefficient. And take a look at this xzzx and yzzzy. On the previous slide, we proved that this coefficient is proportional to our target operator's coefficient. So by summing up these equations, we can conclude that this equation holds. And if this X magnetic field is have non-zero value, we can conclude that this our target operator also has a zero coefficient. And in this way, we can obtain that for all remaining A operators, its coefficient is 0. So after all, we show K local conserved quantity is absent for this Hamiltonian. And this is the summary slide of our finding on spin half systems. And we rigorously show that general spin half system with symmetric nearest neighbor interaction are non-integrable systems in the sense that they do not have non-trivial local conserved quantities. And the exception is the already non-integrable systems. And these theorems prove the ubiquitousness of the non-integrability in this class. So we quickly see the result on spin 1 systems. Here we consider the spin 1 bilinear biquadratic chain, whose Hamiltonian is described like this. The first term is the Heisenberg type interaction term, and the second term is a square of the Heisenberg term. And the model has two parameters, J1 and J2, and essentially the ratio of these parameters is important. And this bilinear biquadratic chain include some famous model, such as AKLT model and the Heisenberg model, spin 1 Heisenberg model. And these two operators are expected to be non-integrable. And this chain also includes some integrable systems whose parameter is like this. And our finding on this model is quite similar to the result on spin half systems. And we show that this spin 1 bilinear biquadratic chain is non-integrable except for already non-integrable systems. And so as shown in this figure, there are three already non-integrable systems represented by green lines. And we show that all other regions are non-integrable. And additionally, we add to the Hamiltonian an isotropic field, and we conduct a further analysis. And in the presence of this field, there is only one integrable system survives, and we show that all the other region is non-integrable. And due to the time constraint, we skip the proof of this, the non-integrability proof of this model. But instead, let me introduce a basis we use in the non-integrability proof. And in the past, the non-integrability proof on spin 1 systems are considered to be difficult. And indeed, the Schleich's first paper says that the extension of non-integrability proof to spin 1 systems looks not straightforward. And the reason is that the computation relation of spin 1 operator is more complicated. But importantly, there is some arbitrariness of the choice of the basis. So we chose the basis according to the two criterion. The one criterion is that that basis has a simple commutation relations. And the second criterion is that the basis should describe the model's Hamiltonian simply. And we found the basis which satisfy these both of two criteria, like these operators. And here is the commutator table of this basis, and we can see that the commutator of any pair of basis element becomes the proportional to the other basis elements. So only single terms appear in each box. So there is some famous 3×3 the basis of 3×3 matrix, Gelman matrix, but Gelman matrix does not satisfy this condition. And by using our basis, the Hamiltonian, the bilinear biquadratic chain Hamiltonian is described by this simple form. Yeah, yeah. It may not be seem to be so simple, but it have a good form to conduct analysis of non-integrability. And let me mention some other recent progress on non-integrability proof. And the first one is on the system on higher dimensional lattice. For general dimension, which is greater than 2, the transverse field Ising model and XY model and Heisenberg models are shown to be non-integrable. And the next one is on higher spin systems. And just before I explained the result on spin 1 systems, but we actually successfully proved that there is some non-integrable system for general higher spin. And we also show that bosonic system. We also showed the non-integrability for some bosonic systems. And on the final slide, let me answer to the frequently asked questions whether the computers can prove non-integrability. And the answer is no for the present. That is because the proving the coefficient as 0 for general K requires some craftsmanship. So it means that the procedure of showing the all coefficients as 0 is chosen manually. But in my opinion, in the future, the non-integrability proof may be done automatically. To explain the reason, let me introduce a conjecture. This conjecture says that the presence or absence of 3 local conserved quantities is coincident with the presence or absence of general K local conserved quantities. And this conjecture is roughly same as the absence of partially integrable systems. And surprisingly, all studies to date support this conjecture to the best of our knowledge. And this conjecture is quite important because once we admit this conjecture, the integrability test, which means that to determine the system integrable or non-integrable, is becomes very easy task for computers because all we needed to do is to check the presence of 3 local conserved quantities. So for now, my biggest research interest is on this proving this conjecture. And this is the summary slide. Thank you for the listening to my presentation.
Okay, thank you for your talk. Questions? Okay. Let me ask. So you say that, for example, in spin 1/2 chain case, we have only XXX, XXZ, XYZ, and some Ising models.
Yes, XY. Did it say that? Yes.
Or also for some J equals 0, yeah.
Yes. And this one. Yes, exactly.
Okay, yeah. So, and this, okay, thank you. So, any other questions?
Probably it's a trivial question, but for example, Hamilton square of Hamiltonian is of course
Yes.
conserved quantity. How is it excluded in your proof?
Yeah, thank you for the question. And so in our definition, the square of the Hamiltonian is not non-local. So that means n½ plus 2 local or some, and we only show that we only show the absence of k local quantities for for k is smaller than n½ so the square of the Hamiltonian is excluded.
So definition of integrability is yeah. Can you show the definition of integrability again?
Yes.
Yeah. So
Yes.
Yeah. Sorry, Mizuki, you should show the main theorem and
Yes.
and show that this k upper bound for k is optimal in this sense. Sorry for interruption.
Sorry, but I don't write this, but this one. We showed that the absence of local conserved quantity for this.
Oh. Okay, I see.
So if you consider the square of the Hamiltonian, it barely breaks this inequality upper bound.
Yes.
I see. Okay. So this definition of integrability is only using local conserved quantities.
Yes, spatially local.
So is that so? How about global conserved quantities?
Oh, so the global. So
I mean, non-local.
yes. So the uh, uh, so eigen the decompositions of Hamiltonians of the two eigenstates. Uh, so so. So all of Hamiltonians have infinite number of conserved quantity, non-local conserved quantity, include non-local conserved quantity. That is we can convince of this fact from that the decomposition of Hamiltonians gives so the Ket-Bra of eigenstates is trivial conserved quantity, but usually it is very high non-local quantity. So we have to make a constraint on the locality of conserved quantity.
Okay, thank you.
Thank you very much.
Okay, let us thank our speaker again.